In this video, we cover the material in Chapter 11. This is the beginning of our study of organic chemistry. We're going to begin studying in some sense, the simplest organic compounds, what are called saturated hydrocarbons. So we'll give ourselves a kind of an introduction to organic chemistry, how we name organic compounds, a lot of details on structure and properties, and we'll look a little bit at some of the chemical reactivity of alkanes, which is really fairly minimal. Organic chemistry involves compounds that contain carbon. And your textbook says there's over 20 million. There's actually well over 20 million compounds that are currently known. And by currently known, that means they've been synthesized or isolated from naturally occurring substances and characterized. And there's actually one published study, and I'll show it during lecture. It calculated the number of possible stable organic compounds that had 17 or fewer atoms, that is, 17 or fewer carbon, hydrogen, nitrogen, oxygen, and sulfur atoms. And they calculated there are over 166 billion possible compounds. So we'll see that organic chemistry is an extremely diverse field, kind of very rich, because it turns out that carbon atoms are kind of like tinker toys, and we can just assemble them in a variety of different ways. And it's very easy to kind of click and move the carbon atoms back and forth. So as we saw in our last chapter, carbon atoms form four bonds, and four total bonds, and the individual bonds that occur tend to be single, double, or triple bonds. Carbon atoms can make long chains, they can make branch chains, they can make ring structures, there can be multiple fused ring structures with chains attached to them, and so forth. And we'll take a look at all of these different types of systems over the next couple of chapters. So alkanes, this is our starting place, and alkanes are what we call hydrocarbons. A hydrocarbon is really a binary compound. It contains only carbon and hydrogen. And alkanes are a specific type of hydrocarbon. They're what we call a saturated hydrocarbon. A saturated hydrocarbon has only single bonds throughout the compound. So there's no double or triple bonds. And in lecture, if you want to go into detail, we can explain why they're called saturated, but it'll become more apparent when we get to chapter 12 what saturated means. So alkanes, the ones that are linear and branched, have a general chemical formula, C sub n H sub 2n plus 2, where n is an integer, 1, 2, 3, and so forth. And so from this, you can calculate what the linear or branched alkane molar mass is, and a variety of other things. Now, when we're going to be looking at alkanes. That means carbon has all single bonds, and if it has all single bonds, that tells you it has four different things attached to it. There are going to be four single bonds. And remember, if you have four single bonds, that's four electron groups. That means the structures are going to be tetrahedral. So we find out that there are lots of organic compounds that have carbon with all four bonds in all of its linkages. Now the simplest one is methane, CH4. It's very common. It's the primary component of natural gas. It's very abundant. And in this case, each of the bonds in methane has a bond angle of 109.5 degrees exactly. Now the atoms do wiggle, so the average is exactly 109.5. At any given instant, the angle can be slightly different. Now larger hydrocarbons can have multiple units of carbon attached together. So an example is shown here. This is octane, Octane involves 8 carbon atoms, and so its chemical formula will be C8H18. And you find out that all the carbons throughout here have a bond angle of approximately 109.5. Now, when you get away from methane, the bonds are no longer exactly 109.5 on average, because the carbon hydrogen the carbon hydrogen bond angles are different slightly than the hydrogen carbon hydrogen bond angles. Now we can represent alkanes, these saturated hydrocarbons, in a variety of different ways. And this table here is something you should spend some time looking at just to get comfortable for these different representations. You'll find that, if you go further in chemistry, if you study biological chemistry or medicinal chemistry or molecular biology, you will tend to use some of these upper forms on this table. We're going to talk about all of them, and I want to start this table at the very bottom. At the very bottom, we have our molecular formula. The molecular formula simply lists the number of each element in the molecule. So for this molecule we're looking at here is butane. That means it has 4 carbons. It's a saturated hydrocarbon. And so the molecular formula will be C4H10. Now if we're dealing with normal butane, as we'll see later on, normal butane just has a straight carbon chain, 4 carbon atoms right in a row. So 4 carbon atoms are connected directly to one another. And so we can draw this as a condensed structure. So we can have a CH3 on the end attached to a CH2, attached to another CH2, and then finally attached to the other side to CH3. And we can represent what we call a condensed structure shown this way. So CH3, CH2, CH2, CH3. And we can do it one of 2 different ways, or as the bottom shows here, CH3, and then in parentheses we can do CH2 sub 2 and CH3. Those are all equivalent condensed structure representations. Now the advantage that the condensed structure has over the molecular formula, and we'll see this later on when we look at isomers, is this tells us how the atoms are connected together. Now next up we can draw a structural formula. That's the third from the bottom. And here this is the Lewis dot structure for this system. So we've drawn the Lewis dot structure. You can see all the bonds shown here. What are all the atom connectivities? This is a very common way of representing molecules, and we'll do this quite a bit when we do organic chemistry. So this gives us a 2-dimensional kind of a cartoon representation, and we have to infer what the bond angles are. But since we all know they're saturated hydrocarbons and all the carbons are having 4 bonds, we know that these are tetrahedral. Each of the carbons is tetrahedral. Now there's a shorthand notation which we often draw. It's called a line angle formula. And this is a little kind of a stick drawing where each point or each vertex in this drawing represents a carbon, and each line represents a carbon-carbon bond connection. We don't draw any of the hydrogens on here because we assume, okay, if we see all single bonds here, we can infer, or we kind of deduce, that the 2 end carbons must have 3 hydrogens and the 2 interior carbons must have 2 hydrogens, because every carbon will have 4 bonds. Now another representation, which is a little more sophisticated and is commonly drawn, and it turns out to be very useful, that is attempting to use kind of perspective drawing. If you've ever done drafting and done perspective drawing, let's take the leftmost carbon here. We have one line going up to hydrogen, one line going down to the lower right to a carbon, and then the other 2 hydrogens are not in the same plane. One goes behind the plane of the paper, and that's the dotted wedge. And then one is coming out from and is in front of the page, and that is the wedge, the solid black wedge carbon-hydrogen connection. So when you look at these, this should help you to visualize the tetrahedral nature of each of the carbons in this system. Now, sometimes computers will generate the upper two, the ball and stick model of the space filling model. We're not going to use those, we won't draw those, but the ball and stick model will look like the molecular model kits that you should have available to you. So we'll take the molecular model kits out and start to put molecules together and give ourselves a chance to, in our minds and then with our hands, visualize what these molecular structures are doing. So all these are just different representations of the exact same molecule. That is butane, or what we'll see later is N-butane, normal butane. Now, this kind of repeats what we've just seen, how we depict these organic molecules. The space-filling molecule, the space-filling model, that is the thing that has all the electron clouds drawn up and then shows balls connected by electron clouds. That's the most realistic representation, but it's kind of hard to see. It's usually useful in computerized systems where you can rotate the molecule and then visualize putting it into a particular receptor or pocket, but we're not going to use those so much. The ball and stick model, this is really a kind of a graphical representation of what our molecular model kits will do, and again, you won't be drawing those very much. Next up are structural formulas. These are very important, and you should be able to draw these. Okay, so solid wedges are indicating when the bond is coming out of the paper. Dashed wedges show it going into the paper, and then radial lines show the bonds that are in the plane of the paper. And this allows us to represent tetrahedral systems, or non-planar systems. The line angle formulas are pretty common. We'll use these some, and these are ones where we just draw the carbon atoms and show their connectivities, and this is actually pretty important. So you should be really good with the line angle formulas, especially by the time we get to the finish of this class. I think you'll be very comfortable drawing line angle formulas for a variety of different organic compounds. And finally, molecular formulas. These are essential and always important for us to be able to write these down so we can represent chemical reactions. Now, condensed structures, these are written on a single line, and they connect the groups of atoms that are written together. So this is a way for us to see how are the atoms connected generally. We know that the hydrogens are filling in the extra valence sites on carbon, so we don't need to draw those necessarily. So that's why condensed structures are important. So here we've got butane drawn three different ways on the right-hand side. And this is all linear butane. So you can show the bonds between the atoms, or you may condense them down without the lines drawn to connect them. But this allows us to differentiate relative to something that is a different compound. So the three on the right-hand side are all the representations of the same compound. That would be butane. But then at the bottom, we have a compound that's sometimes called isobutane, or methylpropane. And so this is a different structure here. And the line formula allows us to see that. So in order to draw line angle formulas for a hydrocarbon, draw bonds between the carbon atoms using zigzag lines to represent the tetrahedral angles. And you can omit explicitly drawing the carbon labels. You don't have to draw C for carbon. The carbon atom is implied at the intersection, or the vertex, and at the end of each diagram. And we omit drawing all the carbon-hydrogen bonds and the hydrogen atoms themselves, because you now know that carbon has 4 bonds, and so you can deduce how many hydrogens are on each system, or each atom. Now, line angle structures can be converted to structural formula by placing the carbon atom at the ends of each line segment and included at each intersection. And we complete the structure by adding bonds to hydrogen to give each carbon a total of 4 bonds. So we can take the line angle structure and build out a structural formula this way if you like. So let's continue with our introduction to alkanes. So here are 3 different representations of a molecule that's called ethane. So this have a formula of C2H6. You can see that we have CH3 bonded to CH3 with a single bond. In A, we've represented it this way. B, we've drawn the kind of more explicit Lewis dot structure. And then C, we have our ball and stick model. So saturated hydrocarbons that contain only single bonds between carbon and hydrogen are alkanes. And alkanes form 4 bonds, and they all have a roughly 109.5 degree bond angle, pretty close to that value. Now the formula for all hydrocarbons, saturated hydrocarbons, alkane, are CnH2n plus 2. So to find the number of hydrogen atoms, you simply double the number and add 2 to it, right? So, here's a case on the right-hand side. We have a molecule we'll see in a moment is propane. It has 3 carbons, and so we know it has 8 hydrogens on it. If we have 5 carbons, then we would have 12 hydrogens for a linear or branched alkane. Now, next up, we're going to learn how we name alkanes. Even if you take something small, something fairly simple like C7H16, seems like a fairly simple compound. There are a very large number of ways that we can connect all those carbon atoms together. There's a simple one where 7 carbon atoms are in a line, but then we can have lots of structures where there's branching or even ring structures within the system. So we have to have a way of systematically naming compounds, that is, communicating to other scientists or engineers what compound we mean explicitly. So we have a systematic way of naming organic molecules based on their structures. We call this the IUPAC system, and we had talked about the IUPAC system in basic chemistry. So for unbranched alkanes, where all the carbon atoms form one straight chain, one kind of continuous chain, they have names that begin with a prefix to tell you the number of carbon atoms, and you put the prefix in, and then you simply add ane to the end, meaning ane means alkane. So an alkane with 3 carbons has the prefix prop, and so we call this propane. Octane has 8 carbon atoms, so we call it octane. So that leads us to this table, and you need to memorize this table. It's similar to the one we had for naming binary compounds in general, but it's really specific to hydrocarbons. So the first 4 entries are different. So it's not mono, it's meth, it's not di, it's eth, and so forth. And so if you have 1 carbon, the prefix is meth, 2 carbons, the prefix is eth, 3 carbons, the prefix is prop, 4 carbons, the prefix is bute, 5 carbons, the prefix is pent, 6 carbons, the prefix is hex, 7 carbons, the prefix is hept, 8 carbons, the prefix is oct, 9 carbons, the prefix is non, 10 carbons, the prefix is dec, 11 carbons, the prefix is undec, 12 carbons, dodec. And it actually does continue beyond there, but we don't need to go beyond there for this class. So if we were looking at alkanes, for example, let's just go from C1 to C12, we would have methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, undecane, and dodecane. Now, linear alkanes can also be kind of rebuilt, and we can make what we call branched alkanes. Now, branched alkanes, they'll have the same number of carbons, but they're not connected linearly or in a straight line, some of the carbons will be off on the side, what we call side chains. So substituents are any atom or group that replaces a hydrogen or a hydrocarbon and creates this sort of what we might call side chain. And in this chapter, we're going to look at the chemistry and behavior of two types of side chains. And the first one are halogen atoms. So think of group 17 in the periodic table. Those are the halogens. Fluorine, chlorine, bromine, and iodine. Now, if you remember, these all have 7 valence electrons. And in many cases, particularly if you're dealing with what we call haloalkanes, they all form one bond. And when they form that one bond, they have a complete octet. Now, I will tell you there are more complex systems where chlorine, bromine, and iodine can form multiple bonds, and we're not going to look at that. And that's not so important for organic chemistry, but it turns out fluorine really does stick strictly to forming a single bond. So these can all replace a hydrogen atom because they can all form one bond. Another thing that can replace a hydrogen atom on a hydrocarbon would be another hydrocarbon, what we would call an alkyl group. An alkyl group would be a hydrocarbon that's missing one hydrogen atom. So that means one of the carbons still has a bond to form, and it can bond to another hydrocarbon chain if you replace a hydrogen atom. And we'll see how this works in just a moment. So alkyl groups are named just like we named in table 11.2. We take the number of carbon atoms, but then we add a YL ending. So for example, if we have just one carbon with 3 hydrogens, we would call that a methyl group or a methyl. If we had 2 carbons, like if we had C2H6, that's ethane, but if we take off a hydrogen, it's C2H5, we would call that ethyl. So if you go down your table, we've got methyl, ethyl, propyl, butyl, pentyl, hexyl, and so forth. And some of the alkyl groups can also contain branches, and they have even special names as well. So here we can see, like we talked about, the methyl group is a CH3 group. The carbon has 3 bonds, but now it needs to make a 4th bond to somebody else, and so we call this a methyl group. If you have 2 carbons, then we have the ethyl group, C2H5. 3 carbons is C3H7, the propyl group. 4 carbons is C4H9, butyl. Now there are some branched versions, and we should mention these here. You should know each one of these. We have the isopropyl group. It looks like the propyl group, but the unbonded, the carbon with needing an extra bond is the center one, not the end one. So we call that the isopropyl group. It's an isomer of the propyl group. Now we can do the same thing with butane. If the butane group is kind of off to the side, as you can see here too. See here we've got isobutyl group, and then there's the sec-butyl group and the T-butyl group. So you should look at those and probably make molecular model kits for each of those just to visualize them. So we know how to name all the linear alkanes from C1 to C12, from methane down to dodecane. Next, let's look how we name branched alkanes. So to name a branched hydrocarbon, we combine the names of the substituent branches with the name of the longest continuous carbon chain. And that longest continuous carbon chain we call the parent chain. So the branches plus the parent chain gives the name. So here, look at this example. At the bottom in I guess it's yellow color, you have 3 carbons in a row. So a carbon chain with 3 carbons, what do we call that? We call that propane. But you notice in this case we've not got a simple propane molecule because the center carbon is not CH2, it's CH, but then it's bonded to a CH3. That CH3, as we just saw, is a methyl group. So we would call this methylpropane. Now, we're going to have to add some complexity to this because methylpropane is simple. There's only one place for the methyl group to go. But if we have something that's a longer chain, we have to say where the methyl group is on the chain. So our first step is the parent name of the molecule is based on the parent chain. That is the longest continuous chain of carbon atoms. Then we assign a set of numbers to each of the carbons along that parent chain. So for example, if we have pentane as our longest chain, we'll have carbon 1, 2, 3, 4, and 5. If you had heptane, we would have carbons 1, 2, 3, 4, 5, 6, and 7. Then what we do is we look at where our branch is. And what we do is we start numbering our carbon chain such that the branch will be at the lowest number. So the example is shown here. Here we've got two nice representations. You can see that the longest carbon chain here is 5 carbons, which makes it a pentane. And we could either, we've got a branch off of the second to last carbon, so we could number it 1 to 5 where the branch was at 4, but we could also number it where the branch is at 2, and that's the correct way to do it. You give it the lowest number. That's the accepted formalism, and so that is what you should do to communicate properly. 4-methylpentane, if you went to look that up in the American Chemical Society database or SciFinder Scholar, or you went to look anywhere, you wouldn't find anything because we don't call it 4-methylpentane. It's called 2-methylpentane. Next up, if we have 2 or more of the same substituents, then, for example, if we had 2 methyl groups on there, we would call it dimethyl. If we had 3 methyl groups, we'd call it trimethyl. If we had 4 methyl groups, we'd call it tetramethyl, and so forth. So here, we actually use the prefixes from the table in Chapter 5 that you learned earlier. So we have to indicate the number of each methyl group on the system. And so each substituent has a location number, even if they're on the same carbon. And then we have to say how many of those that we have. So for example, if both of the methyl groups were on position 2, we would call that 2,2-dimethylhexane. But in this case, of course, we don't. We have one on position 2 and one on position 5. So you can see in this picture here, our longest carbon chain has 6 carbon atoms. So we call this a hexane. There's 2 methyl groups off at substituent 2 and substituent 5. Or position 2 and position 5. So we call this 2,5-dimethylhexane. Now, what happens if we have multiple alkyl groups on the sides, but they're not the same length? So we still pick out our longest chain, but then what we do is we have to list all of the different alkyl chains. We don't list them in numerical position, we put them in alphabetical order. So for the picture here, if you look at this, you can see that the longest continuous chain of carbons has 9. So you follow that yellow pathway, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then we can see that we have a methyl group on position 3, an ethyl group on position 4, and a propyl group on position 5. So the 9 carbons tell us it's a nonane. And then we have our methyl, ethyl, and propyl, but the first one alphabetically is ethyl, the second one is methyl, and the third is propyl. So we would number this 4 ethyl, 3 methyl, 5 propyl nonane. Make sure you're comfortable with these naming approaches. We'll do some in class, and you'll have problems to solve where you have to name or identify structures for names. So finally, the substituent location numbers can be omitted if there's no question about where the system is located. So, for example, methylpropane, there's only one place for the methyl to go. So we don't need to call it 2-methylpropane. Next up, we're going to look at a variant on alkanes, and these are what we call cycloalkanes. Cycloalkanes, these are still saturated hydrocarbons, and so each carbon will have 4 bonds, but the carbons are connected in a ring structure. So there's not necessarily a terminal unit unless we have a branch on the side. So for simple cycloalkanes, they're a ring. So you can't have, of course, cyclomethane because there's only one carbon. You can't have cycloethane, but the smallest one we can have is cyclopropane. So we can have cyclopropane, cyclobutane, cyclopentane, cyclohexane, cycloheptane, and so forth. Cycloalkanes, then, are saturated hydrocarbons that contain a ring of connected carbon atoms. And to kind of delineate this, we simply add the prefix cyclo onto this. Now, one thing you'll notice if you go through and kind of count up your hydrogen atoms, you'll notice that without the terminal CH3 units, we have fewer hydrogens in this. So cycloalkanes have the general formula CnH2n. This contrasts with linear alkanes, which are CnH2n plus 2. The number of hydrogen atoms is simply double the number of carbon atoms in the simple cycloalkanes. So cyclopropane is C3H6, cyclobutane is C4H8, cyclopentane is C5H10, cyclohexane C6H12. And you can see here we've got our structural formulas or our line representations. Either one of these is good to show us what we have. I want to make one quick side point on here. For the saturated hydrocarbons that are not branched, the bond angles are 109.5. But for the cycloalkanes, they are not. You can see in this case, for example, cyclopropane, the carbon-carbon bond angles are 120 degrees, not 109.5. We can have substituted cycloalkanes as well. And so we can replace a hydrogen on the cycloalkane with an alkyl group. And here we've got 3 examples. We've got cyclopentane, that is, there's 5 carbons. We can replace, we've got a bunch of CH2 units. We can replace a hydrogen with a methyl or an ethyl or a propyl and so forth. So if only one substituent is present, if we go to name this, we don't need to say where the position is because, of course, there's only one. So methylcyclopentane, there's just one there. So if we have multiple substituents, the ring is numbered sequentially to result in the lowest set of numbers, and the first carbon is always has a substituent on it. So for example, if we have 2 methyls on cyclopentane and they're at different positions, we would have 1,2-dimethylcyclopentane, for example, as shown in problem B. Now, in C, here we've got a methyl and an ethyl. And so, of course, who gets named first? the first alphabetical system, which would be ethyl in this case. E comes before N. So we have 1-ethyl, 3-methyl cyclopentane, giving us the lowest number. Haloalkanes, and as like we said before, we can replace the hydrogens with halogens, and these are very important compounds. You see them all over the place. Chloroform, dichloromethane, CFCs, lots of very important compounds, halons. A lot of very important compounds are haloalkanes. And so we've got halogens substituting for the hydrogens. So halogen substituents are named using the root name of the element plus O, so fluoro, chloro, bromo, or iodo. And then we use the parent name for the organic compound, the alkane. And we use the same guidelines to number and alphabetize the alkyl groups just like we did with the alkyl groups. Okay, and we'll do a bunch of practice problems in class to go over naming of linear alkanes, branched alkanes, cycloalkanes, and haloalkanes. And you should also be comfortable drawing their structures. So next up, we're going to look at the properties of alkanes and haloalkanes. And the first thing we're going to talk about is simple hydrocarbons. Now, in thinking about the dipole moments, we can take something simple like methane, and if you looked at methane, you would deduce that it has no dipole moment. The carbon-hydrogen bonds are mildly polar. There's a 0.4 electronegativity difference for each of the bonds, so that they're slightly polar, with the hydrogens being slightly positive and the carbon being slightly negative. But they're pointing at the four ends of a tetrahedron, and so they all cancel out. And so overall in net, methane is not polar. So it turns out that this is general for hydrocarbons. Simple hydrocarbons do not have dipole moments. They're nonpolar overall. And this has a really important impact on how they behave. Now, this slide covers something called intermolecular forces, and we've not discussed these to this point. We'll take a little detour during lecture in class to cover this, but let me just say here that you can consider a molecule itself, and within that molecule or within that compound, there are forces between atoms. There's ionic bonds in ionic compounds, and there's covalent bonds in covalent or molecular compounds. And those are all, ionic bonds and covalent bonds are very strong forces. But it turns out that there's another group of forces. They're much weaker, but they can be very important. They're what we call intermolecular forces. And let's take a very simple case. Let's take methane and methane. Two methane molecules can actually attract one another very slightly. They'll just very slightly hold one another together, not strongly. There's a very weak interaction. But they do interact with one another. And that's actually what holds things together in the liquid state, is the intermolecular forces. And there's a series of intermolecular forces. The strongest ones are ion dipole forces and hydrogen bonding forces. But there are some weaker ones. And the weakest intermolecular force is what we call a dispersion force. And the dispersion force is when I have two neutral non-dipolar molecules, or atoms, for example. And they will interact through these weak dispersion forces. So these dispersion forces are the only thing that happen in hydrocarbons. Water, in contrast, has a dipole moment, plus it has something called hydrogen bonding. And so water has a very unique set of properties that causes it to form really spherical droplets, to have a very high surface tension, very high heat of vaporization, and so forth. Alkanes don't have that. They're held together much more weakly. Now, Dispersion forces are weak, but they do increase as the molecule becomes larger. So larger hydrocarbons have stronger dispersion forces than do smaller hydrocarbons. And if you want to look at this in a lot more detail, you can go to your textbook and it will discuss intermolecular forces. So now as we just look at the dispersion force trends, not including any other force, just the dispersion force, it turns out that there's a number of factors that affect this. The shape of a molecule affects the strength of dispersion forces. So molecules that are kind of unbranched or flat or elongated, they tend to have more kind of a larger dispersion force because there's more surface area by which molecules can contact one another. So unbranched hydrocarbons have stronger dispersion forces than branched molecules of the same molar mass. But then molecules that have larger molar mass have larger dispersion forces. And in summary, for hydrocarbons, the melting and boiling points of compounds increases with increasing intermolecular force, and the intermolecular force increases with the molar mass or the size of the molecule. So small alkanes have very weak forces, and they're gases at room temperature. Slightly larger alkanes are liquids, and then the very largest alkanes, they're like wax. So wax is a very large alkane, and that is a much larger molecule, and so the dispersion forces add up and hold the system together more. So melting and boiling points of a series of alkanes are shown here: methane, ethane, hexane, hexadecane, and tetracosane. This just shows the formula. You wouldn't know the name tetracosane, but it's C24H50. It's a very long hydrocarbon, right? And you can see the melting points increase as the molecule gets bigger. The boiling point increases. And then the state of matter at room temperature goes from a gas to a liquid to a solid as we increase the size of the system. Hydrocarbons, being driven by dispersion forces and being nonpolar, they tend to dissolve in other nonpolar solvents. So let's take wax as an example. Wax is just a hydrocarbon with a long molecular mass, or a long chain or high molecular mass. So they tend to dissolve in nonpolar solvents like mineral spirits or gasoline. But they don't dissolve in polar solvents like water. So there's a general statement: like dissolves like, and if something is nonpolar, it will be dissolved by nonpolar solvents. It will not be dissolved by polar solvents. Hydrocarbons have weak intermolecular forces, and that doesn't hold them together very tightly when they're in a liquid, so they tend to evaporate quite easily. They have low enthalpies of vaporization. They boil quite easily. And finally, the density of most hydrocarbons is relatively low. Most hydrocarbons have a density of about 0.8 grams per mil, which is less than that of water, which is 1 gram per mil. So hydrocarbons don't dissolve in water, and they tend to float on top of water. So if you take gasoline, it'll float on water. It's primarily alkanes. If you take hexane, it floats on water and does not dissolve. So that's the physical properties: the solubility, the boiling point, the melting point, and the density. The next couple of slides we're going to look at are the reactions of hydrocarbons. And it turns out that saturated hydrocarbons are just not that reactive. They don't chemically react very much. They actually work as solvents. They're very good solvents for chemical reactions because they don't interfere. They don't react with anybody. They tend to be very low reactivity systems. So alkanes are low reactivity systems. It's kind of hard to break the carbon-hydrogen bonds. They're stable. And carbon atoms at the center, they're blocked by lots of things. This is tetrahedron, so it's hard to get to the carbon, so they don't do much. But one thing that hydrocarbons do is they burn. And, So we don't think of gasoline as being, or hexane, things like that, mineral spirits as being unreactive, but that's just because they can catch fire. And when alkanes react with oxygen, they form carbon dioxide and water. That is when there's ample oxygen around. Now, if the surroundings are a little bit oxygen deficient, the combustion is not complete. And so these are the second two reactions here are the other two pathways. Your book only talked about the first one, but the second one is probably one you might even have encountered more often. Here's the reaction of ethane with oxygen. And if the oxygen is short, you can get carbon monoxide, or you can get soot produced. And you've seen this before. If you burned a candle, you've seen a sooting flame. You see little bits of black material sometimes wafting away from the flame. That's when there was a moment when the flame was in an electron or oxygen deficient state, and so the wax didn't burn completely. So it turns out that when you design a gas stove or a gas furnace, you typically use natural gas, which is primarily methane, and then a little bit of ethane through butane as well. And it's very important to make sure that the systems are clean and plenty of oxygen is available so that you don't build up carbon monoxide. Because carbon monoxide, of course, is a toxic material, and you don't want to be around carbon monoxide if at all possible. So combustion is the first reaction. There's 3 different combustion reactions: complete combustion to CO2 and water, or partial combustion to carbon monoxide and water, or carbon and water. And the next reaction we're going to look at is the reaction with halogens. It turns out that we talked about redox reactions back in basic chemistry. Combustion is a type of a redox reaction where the alkane is the reducing agent and oxygen is the oxidizing agent. But likewise, you can react with halogens. So you can take an alkane plus a halogen like fluorine or bromine or chlorine or iodine, and the alkane is still the reducing agent, but then the halogen becomes the oxidizing agent. So alkanes can react with elemental halogens like chlorine, bromine, iodine vapor, or fluorine. Typically, you need a high temperature or UV light to get the reaction to start. Just like we need a spark or intense light to get combustion to start up, we need same thing for haloalkane formation. So this reaction is one of the first, I guess this is one of the kind of our introduction to organic reaction nomenclature. We call the reaction between alkanes and halogens a substitution reaction, because a halogen substitutes for a hydrogen in the system. So here we've got one where we're not using a spark or heat, we're using ultraviolet light. So we use high energy light to break the carbon-hydrogen bond and to get the reaction going. In the first case, we have methane plus limited amounts of bromine vapor. We end up with methyl bromide plus hydrogen bromide. But if we add enough bromine around, we can replace more than one. And so your slide here shows you replacing one, but you can replace 2 or 3 or all 4. And typically, if you do this sort of reaction, this is not a very, what we call selective reaction. It's kind of uncontrolled. And so you turn on the UV light and you just start replacing the bromines, and you go until you're finished, and then you have to separate out your final product. So it's not easy to do this reaction to produce exactly 1 or 2 or 3 bromines. We have to do separation later on. So the reaction is an alkane plus your bromine to give your your halogenated alkane, and your other product is hydrogen bromide. Now you'll notice the second reaction shown here is not properly balanced. We'll look at balancing those in class. Next up, we're going to look at a specific, so we've covered the structures of alkanes, naming alkanes, their physical properties, and their chemical reactions. The last thing we need to look at are what we call isomers. This is a unique angle that we've not come across so far. In basic chem, we didn't really discuss isomers in significant ways. Isomers are different compounds that have the exact same molecular formula, but there's something different about their structure. So there are structural isomers. That just means that the atoms are connected in different ways. And so branched alkane versus a linear alkane that has the same formula would be a structural isomer. But there's also something called a stereoisomer. And stereoisomers have all the same atoms and all the same connections, but they differ in three-dimensional space. So there are a couple of types. There are what we call cis-trans isomers, and then there are enantiomers. And we'll talk about each of those in turn. So let's start off with the easiest one, the structural isomers of the alkanes. So alkanes that have 4 or more carbons can have structural isomers. You have to have at least 4 carbons, because if you have 3 carbons, they've got to be in a straight line. That's it. So as the number of carbon goes up, it turns out the number of possible isomers goes up. So here we can see, in this figure, you can see the 3 different versions of the 5-carbon system. C5H12. Well, you might think C5H12, that's pentane, right? 5 carbons in a row. But I can have butane with a methyl group on the 2 position. So this is methylbutane. Methylbutane has the exact same molecular formula as pentane, but it has different chemical properties. And then also we can have 2 methyl groups, both of them off of a propane chain, and that's dimethylpropane. So here's 3 compounds all having the exact same molecular formula, C5H12, but they're different compounds with different reactivities and different physical properties. Pentane, methylbutane, and dimethylpropane. These are all examples of structural isomers. So while they have the same number of atoms, they have a different name and different sorts of different behaviors. Now, as we're going on, we need to stop and discuss one side point, and that is what we call the conformation of an alkane. Turns out atoms connected by single bonds can actually spin around. And when we get our molecular model kits, you'll see this. You can make, for example, here is butane. You can make butane and you can get the groups to rotate freely. And that happens in the molecule. You can actually see these molecules rotating. They look like propellers in some cases. They don't behave like propellers for reasons we can discuss in lecture, but they look like a little propeller. They rotate. So in figure 11:12, this shows you butane, and it shows you conformational variations. Now, conformations are not isomers because none of the bonds are broken, and this is just the molecule kind of moving around. It's one single molecule moving into different shapes. It's like if you stood up, you'd be in a different position. You're still the same person. If you raise both of your arms over your head, you're a different shape now, but you're still the same person. Next up, we're going to look at cycloalkanes, because these show a very specific type of isomerization called cis-trans isomerization. We'll see this later on for alkenes, and this becomes very important for their systems. So atoms in ring structures have a peculiar behavior. They can pucker and move a little bit, but they can't rotate freely. Linear alkanes can kind of rotate. Cyclic alkanes can't. They're locked in place. So what that means is, if I have multiple substituents, so multiple sort of branches off of the cycloalkane. So, for example, in this picture here for figure 1113, I've got the dimethyl cyclopentane. The methyl groups could both be on top of the cycloalkane, or one can be on top and one can be on bottom. Now, if they're both on the bottom, that's the same as both on the top. That's actually exactly the same thing. But they can be up and down. So if they're both on the same side, we call that a cis isomer. If they're on the opposite side, we call that the trans isomer. Okay? So when we name the compound, we need to delineate. If we have multiple branchings, we need to delineate up versus down. Now, if there's multiple substituents, more than two, this becomes more complex, and we're not going to dive into that naming scheme in this class. Okay. Now, let's go back here. Cis 1,2-dimethylcyclopentane and trans 1,2-dimethylcyclopentane, those are isomers, and they actually have different properties in terms of their physical properties. There's slight variations in their physical properties and their chemical reactivities. But the next thing we're going to look at is what we call an enantiomer, and these are mirror image structures where all the atoms are connected identically, except in three-dimensional space, they're connected oppositely. And so the first place to start thinking about this is just look at your hands. You have hands, and you've got a left hand and a right hand. They're both the same, I mean, there's obviously variations because you're human, and we all have, maybe lose a piece of a finger or, damage to one side or the other, so we can tell the difference. But in an ideal sense, the two hands would be identical, except they don't match the same in three-dimensional space. They're opposite from one another. They're not superimposable. So if you take both of your hands palm up and you put the left on the right or the right on the left, they don't match. Okay? So this is what we observe with some molecular systems. So look over on your figure 1114. You've got a carbon atom in the center, that's the red one, and then you've got A, B, C, and D, 4 different atoms connected. Now we would need to have 4 different functional groups here for this to occur properly. If you look here, you can see A, B, C, D are all attached, and then you can see in the mirror you've got A, B, C, D are attached, but they're the mirror image. This is called an enantiomer, okay? And these systems will have identical chemical reactivity and identical physical properties. Their boiling points, melting points, heat capacities, thermodynamic properties are all identical. The only time this becomes apparent is if you take and interact with another molecule that has a mirror image. Then you can start to see differences. So these are what we call chiral molecules, a pair of molecules that are chiral, that is, they're not superimposable with one another. They're mirror images of one another. They're enantiomers. Enantiomers have, it says here nearly, but they actually have identical physical and chemical properties. But it turns out they interact with plane polarized light differently. The only place you start to see differences in their chemistry is when they react with something that has itself an enantiomer. And a lot of the molecules in our body, they're chiral systems. And so then you'll find out that some molecules that are chiral or interact with your body in very unique ways because the receptors in your body are chiral. And so one enantiomer may react and have the effect of a positive effect of a drug, and the other one could be highly toxic. And there are a number of examples. We'll discuss these in a lecture. Okay. So a chiral molecule contains a tetrahedral atom. And generally it's carbon, and that's what we're going to be concerned with in this class. That is carbon that's bonded to 4 different groups. So in our last slide, of course, we had carbon connected to A, B, C, and D, and so they can be connected in a mirror image fashion. To identify a hydrocarbon, you always look and find, is there a carbon bonded to 4 different groups? And sometimes we'll put an asterisk next to them just to make it clear. So in this figure here, you can see A has 4 different groups: hydrogen, chlorine, methyl, and ethyl. And the second one is not chiral. So there's an enantiomer for A. There's not one for B. Okay, and this is a good case for molecular models. You can actually make 2 different molecular models for enantiomers and see how they look. And enantiomers are metabolized differently simply because your body has enantiomers within them. So a lot of your proteins and biological structures are enantiomers. They have a handedness. And so molecules that have 2 enantiomers will react or interact differently. So here's an example: dextromethorphan and levomethorphan are enantiomers. And dextro is for the one that is right polarizing, and levorotatory is left polarizing. And one turns out to be a cough suppressant, and the other one is a controlled substance that interacts with opiate receptors in your body. So that's kind of covering our first chapter on organic chemistry. And as we finish this up, we'll cover our stuff in lecture in more detail and do some practice problems.